Let's look at infinite limits of rational functions, involving rational functions. Before we start, we need to discuss the degree of a polynomial. Now, I know you learned this, but I want to review it. If I have a polynomial p of x is equal to a sub n x to the n plus a to the n minus 1, x to the n minus 1, all the way down to a sub 0, the degree of the polynomial is n. All right, so you're going to need to be able to pull out the highest degree, or the degree of every polynomial we're dealing with. Now, the guidelines for finding the limits at plus and minus infinity when you have rational functions involves you're looking at the degree of each polynomial, the one in the numerator and the one in the denominator. Now, suppose I have a function f of x is equal to p of x divided by q of x. And let's say p of x is of degree n, and q of x is of degree, let's call it m. All right, if we take the limit as x approaches infinity of p of x divided by q of x, what you need to do is look at the order, or excuse me, the degree of the polynomials. If the degree of p or n is less than m, then that means this limit is going to go to 0. Think about what that means. This has maybe x cubed, and this has x to the 5th. The denominator is going to grow much faster than the numerator, even though they're both going to go to infinity. Now, if m is less than n, then this limit is going to go to either positive or negative infinity. Basically, it doesn't exist. But we may say it goes to positive infinity, negative infinity, or does not exist based on the signs of the leading coefficients. Now, if m equals n, then the limit as x goes to infinity of p of x divided by q of x is a number. It's L. And that L is equal to a sub n divided by b sub m, the leading coefficients of p and q. It's much easier to do them. Let's look at this function right here. For this function, p of x is 2x plus 5. It is of degree m equals 1. Q of x is 3x squared plus 1. Its degree is m equals 2. So when I do this limit, the limit as x approaches infinity of p divided by q, because the degree of the numerator is less than the degree of the denominator. Oops, that's an m. Because that's true, this limit is 0. We can also say this has a horizontal asymptote at y equals 0. Now let's look at this one. P has a degree of 2, and so does Q. So for this one, you just look at the leading coefficient. So it turns out none of the rest of it really matters. So this limit is 2/3. So we can say this has a horizontal asymptote of y equals 2/3. You're going to get really fast at these. Let's look at this one. Oh, we did this one. Let's look at this one. This has a larger numerator, or has a larger degree in the numerator than in the denominator. So as x goes to positive infinity, this is going to approach positive infinity, which again, you remember, just means it does not exist. It becomes unbounded in the positive sense. Now you can see it does have a slant asymptote, and we will do those in class.